Hello, and welcome to my talk on bridging the gap between protoplanetary and debris disks. My name is Arnaud Michel, and I'm a graduate student at Queen's University. This work in particular was done with Nienke van der Marel and Brenda Matthews, and our paper has been submitted to AppJ. It's currently under revision, so any comments and feedback would be most appreciated. So we know that the star and the planet formation processes are quite intertwined and include a disk. And so as seen in this cartoon evolution, we're particularly interested in what's happening at these later stages between the protoplanetary and the debris disk. So we asked two key questions. How do disks evolve between the protoplanetary and debris disk phases? And what mechanisms drive the dust growth and disk evolution in these later stages? So there have been many past studies of protoplanetary disk dust masses across star-forming regions. Here we have a cumulative distribution fraction plot against the dust mass for different star-forming regions. And we can see that as their age increases, the disk dust mass distribution decreases. What's most notable for us here is a range of masses ranging from 10 to the 3 to 10 to the -1 Earth masses. When we compare it to the debris disk dust mass evolution in time, we can see that for this plot of dust mass against host star age, there's a decrease. But what we're particularly interested in is the fact that the debris disk dust masses start around 0.1 Earth masses, which corresponds to the tail end of the protoplanetary disk dust masses. And so this is a junction point that we want to investigate further. And some people have already looked at this. So previous studies on late disk evolution primarily use the dust mass as a function of age, seen here in both plots, and show that around 10 million years, there's a dramatic decrease in the dust mass of these disks. And then we're finally into the debris disk phases. And most recently, there've been new studies on late disk evolution, such as Lovell et al. 2020, where they present a new sample of lupus class 3 disks with very low upper limits for their disk dust masses. And they're trying to piece together this protoplanetary to debris disk evolutionary process too. We thus set out to investigate this further. We build our sample of class 3 disks across 11 low UV star-forming regions of ages between 1 and 12 million years. We collect stars with infrared excesses, and we use Gaia parallax to confirm their membership. Of this, we reach a full sample of 704 class 3s out of 3,124 YSOs, and we collect ALMA sub-millimeter or millimeter observations from the literature in the ALMA archive for 91 class 3 disks, so of which we have 71 upper limits. And we plot our first order dust mass, millimeter dust mass comparison of class 2, 3, and debris disks on this cumulative distribution fraction plot as a function of millimeter dust mass divided by the star mass. So here we plot in green the debris disks, the sample from Holland et al. 2017, our class 3 sample that we've collected. Then we have the upper SCO class 2 disks from Barenfeld et al. 2016, and then lupus class 2 disks from Asdal et al. 2016. And so we can see on a first order result that as we go from class 2 to class 3s to debris disks, and as the star forming region ages, the disk dust masses decrease. But when we want to use ages, we find that ages are uncertain, and determining individual object ages are quite hard. And here we plot the dust mass against the age of individual objects for two different models, and we find no clear correlations between the dust masses and the age. So instead, we use a fractional disk luminosity as a proxy for age. The disk luminosity is here the shaded yellow part, which is the excesses from 1 to 110 microns divided by the stellar flux. And so this is a common parameter that's used to study debris disks. And so we'll be applying to both the class 2 and 3, as well as our debris disk samples. So we build a millimeter disk dust mass plot as a function of fractional disk luminosity, where we first have our lupus class 2 objects as well as our upper SCO class 2 objects. And we can see that for a very narrow range of fractional disk luminosities, we have a very large millimeter disk dust mass distribution. And what's most notable is that at the top of this dust mass distribution, we have the structured disks, which we qualify as being transitional ring disks for which we can see the gaps with the ALMA millimeter images. And so there's definitely a different process that's driving the disk dust evolution in this class 2 phase, which we'll come back to later. Then now we have our class 3 objects that populate the lower end of the class 2 disk dust mass distribution and extend in their fractional disk luminosity. This is followed by the debris disks later on. We can see that the debris disks have much lower millimeter disk dust masses, both because this is expected with the evolutionary process, but also because these are much closer, and so the sensitivities are much lower, allowing for better detections at lower disk dust masses. And so the processes that are governing the disk dust mass evolution in the class 2 objects, we propose are mainly radial drift and dust growth. And what particularly separates these structured objects with the remaining disks is that these structured objects are believed to have pressure bumps. And so we see these in the gaps and the rings, and these pressure bumps efficiently halt radial drift. And so this was explored in models by Pinilla et al. 2018 and 2020. In comparison, most of the other disks are radial drift dominated, and so their millimeter dust mass drops rapidly. And by the time the gradual fractional disk luminosity process is taking place, they end up in the tail end with low millimeter disk dust masses and lower fractional disk luminosities. And so this is what we call a gradual disk evolution, where the disks are undergoing dissipation. Furthermore, when we look at this fractional disk luminosity, we see that it evolves with a mass accretion rate. So here we have a plot of the log of the mass accretion rate against the log of the fractional disk luminosity for class 2 objects. And we can see an excellent correlation between these two parameters, indicating their link. And this is concurrent with the mass accretion rate across different regions, where it can remain high even for older star-forming regions, such as Upper SCO, here seen in results from Manara et al. 2020. Upper SCO mass accretion rates appear to be on the same level as lupus, thus indicating that this mass accretion rate is a gradual process that can last a long time. And then recent dust evolution models with low alpha viscosities and radial drift show moderate drops in mass accretion rate while the millimeter dust mass rapidly evolves. And so we see this in Selleck et al. 2020, which helps us explain this picture of how the radial drift is an independent process from the disk dissipation and evolution. However, now we can look at what's happening with these structured disks, which hinder the radial drift. And so we posit that these are the progenitors to debris disks. Since we have these possible pressure bumps that are trapping dust at large orbital radii, they can basically grow the dust in these rings into planetesimals. Eventually, when the gas dissipates, this provides an alternative evolutionary pathway where planetesimal belts at large radii undergo a collisional cascade and form a debris disk. However, the other remaining class 2 disks, which are radial drift dominated, cannot form planetesimal belts at large radii because their dust is just drifted inwards. So I'd also recommend going to see Nienke van der Marel's talk, which also looks at this possible evolutionary pathway in connection to exoplanet demographics. So what does this mean? We see that the millimeter disk dust mass evolution is linked to radial drift and dust growth, but not disk dissipation. And then the fractional disk luminosity evolution is a small dust in the gas, which evolved through disk dissipation in a gradual way. The gradual disk evolution, however, suggests long characteristic disk timescales. So how do we reconcile this plot from Mamajek 2009, where we have the disk fraction as a function of star-forming region ages? And so this fit yields a timescale of 2.5 million years. But what about external photoevaporation? Here seen on the right, we have the disk fraction as a function of time, and we have the disk fractions here in solid lines when they're far from an O star. And when these disks are close to an O star, we can see in the dashed lines a dramatic drop in disk fractions. And this has been well explored in several papers. And so when we look at Mamajek et al. 2009, we can see that there's many O stars in these later regions. And so we've got updated disk lifetimes for low UV regions, where we find characteristic Mdust disk lifetimes on the order of 7 to 9 million years. So this brings me to my summary, is that we've seen that the millimeter disk dust mass evolution in class 2 disks, it's radial drift and dust growth, not disk dissipation. The fractional disk luminosity evolution is a small and the dust gas, which evolves through slow disk dissipation in a gradual process. Then we have different dust sizes evolving by different processes. We also have two evolutionary scenarios: structured disks that could explain the observed debris disks, and then radial drift dominated disks, which would become bare photospheres. We also derive longer disk lifetimes in low UV environments on the order of 7 to 9 million years, which are consistent with gradual disk evolution and low alpha viscosities. In essence, these results set the scene for a novel view of disk evolution. Thank you very much.